All right, let's keep working on 4.1. This is 4.1 part 2. Okay, so the mean is going to be a little different with a discrete random variable. We've been used to a mean being an average. This is going to look a little bit different. What we're going to do is multiply the random variable x times the probability and then add all of those up. Now, luckily, StatCrunch is going to take care of this for us. So we have a probability distribution here. This is for that inventory test with the passive-aggressive traits. So we had scores of 1 through 5. We had probabilities. This is the same as that other problem. We could do this by hand. This shows you how to do it by hand. But why do that when we have StatCrunch? But you can see what they did was they took x, so they took the random variable x, they multiplied that times the probability, and then they added those up to get the mean. But let's go ahead and look at StatCrunch. Okay, so with StatCrunch, you're going to go ahead and hit that little box next to the data so that the data comes in for you. If for some reason there's not a little StatCrunch box next to the data, you'd have to type these two columns in. So once you hit that, you are going to go up here to Stat. Okay, so you're going to click on Stat. You're going to go to Calculator and all the way down here to Custom. Okay, you're going to put the scores in for the value. So X goes in for the value. This is a drop-down window. You're going to put the probabilities in for the weights, and then you're going to hit Compute. Once you do that, the software is going to do the work for you. So down here, you've got your mean in that box. Once you hit compute, you've got your standard deviation here of 1.27, and you are good to go. Oh, let's talk about real quick what that means. So our mean is 2.9. That means the average score for this group of data was at 2.9 marks. Remember, the scores went from 1 to 5. And then our standard deviation was 1.27. Don't panic when you see these formulas. We're not going to be doing these formulas. We're going to let StatCrunch do the work for us. But remember, StatCrunch only gave us standard deviation, right? They gave us the sigma, the standard deviation. They did not give us the variance, but that's okay. The variance is just the standard deviation squared. So that last problem, they gave me, the standard deviation was 1.2713772. So let's round it to 1.3. And so I would answer that as my standard deviation. However, if the problem said they wanted variance also, what I would do is I would not take the 1.3 because of round off error. I would go ahead and go 3 decimal places just to be on the safe side. So I would take 1.271, that's from my standard deviation that StatCrunch gave me. I would square that in my calculator, and that would give me the variance. And so the variance would be 1.6. So when we use Calculator Custom for these probability distributions, we are going to take the mean and the standard deviation right from StatCrunch. If they also ask for variance, we are going to just square the standard deviation. All right, this is showing you the same thing. Don't do all this crazy work. Use StatCrunch. When we use StatCrunch, we had a standard deviation of 1.271. We squared that, and that gave us the 1.6 that we needed for the variance. Okay, for expected value, that is actually the mean. Okay, so for expected value, sometimes we're going to do these by hand, sometimes we'll let StatCrunch do it. But if you see those words, that just means the mean of the random variable. All right, let's take a look at this expected value. So we have a raffle. We have 1,500 tickets that are sold, and they're sold for $2 each. And then you can win one of 4 prizes. You can win $500, you can win $250, you can win $150, or you can earn 75 or win 75. Otherwise, you're not going to win, right? So only 4 tickets are actually winners. The rest are losers. So let's set up our table. Now, the thing is, you paid $2 for the ticket. So if you win the $500, you didn't really win $500. You won $498 because you spent $200 for the ticket. So I could win $498. I could win $248. That's the $250 minus 2. I could win $148, or I could win $73. Okay, but I only have a 1 in 1,500 chance of winning each of those, right? Because one ticket's going to win 500, one's going to minus $2, one's going to be the next. So there are 4 winning tickets. They each have a chance of 1 out of 1,500. If I don't win one of those prizes, I'm going to lose my $2. So that's a negative 2. And all the rest of the tickets are losers. So 1,496 tickets, which is 1,500 minus 4, are losers. All those people are going to lose the $2. Okay, so to find the expected value, we are going to multiply each of these columns. So look down here. I've got $498 times 1 over 1,500, $248 over 1 over 1,500, all the way across. And it gives me an expected value of negative 1.35. So my expected value is that I'm going to lose $1.35. Now, there's no way for me to actually lose $1.35. So what this is if I did this raffle over and over and over again, I would win some of the time. Most of the time I would lose. And so overall, I would lose $1.35. Okay, this is how casinos keep track of what they're doing, because they want you to lose overall. They let you win occasionally, but overall, they want you to lose. And so they use expected value to figure that out. All right, let's take a look at a probability distribution here. So we've got the number of televisions. We have 0 TVs, 1 TV, 2 TVs, 3 TVs. This is talking to different households in a small town and seeing how many TVs they have. So the first thing they want me to do is come up with the probability distribution. So I do need to go ahead and add up how many households I have, because they didn't tell me in the problem. So if I add up this second row here, I get 2,590. And now I can create a frequency distribution, just like we did in chapter 2. So for the first one, I have 24 households over 2,590. Then I have 441 households over 2,590, and so on. So I'm able to create my probability distribution by finding each of those probabilities. Remember, that's the same as our relative frequency. Now notice, now we have to pick a graph, but notice these are all getting bigger and bigger, right? We have 0.009, we have 0.170, 0.278, 0.542. So these the bar chart, the bars need to keep getting bigger and bigger. And so that would be C. And then finally they say, okay, what's the shape? Is it symmetric? Is it skewed left? Is it skewed right? So this one's skewed left. Remember, it's where the tail is. And so since the tail is here on the left, the histogram is skewed to the left. All right, these numbers are a little different, but it's the same idea. It's the number of televisions per household. They went ahead and gave us the probability. We don't have to come up with it, but it asks you if it would be unusual for a household to have no HD televisions. So for it to be unusual, the probability has to be less than 5% or less than 0.05. So this would make a probability unusual. Well, for 0 TVs, we have 0.02. So that definitely is less than 0.05, and so this would be unusual. So basically I have 2% versus 5%. 2% is less than 5%. And this is very close to zero. It's very small. And therefore, it would be unusual to have no HDTVs for this data set. All right, this one's asking me if this distribution is a probability distribution. So if we look at it, each of the probabilities is good, right? They're between 0 and 1 inclusive. I don't have any negatives. I don't have anything greater than 1. But if you put that in your calculator and add those up inside your Casio, you get 0.91. That is not going to work. Those probabilities need to sum to 1. This one does not, and so we're going to say no, it is not a probability distribution. Okay, so they gave me another probability distribution. I've got the number of dogs per household from 0 dogs up to 5 dogs. They went ahead and did the probability for me. That was very nice. And they want the mean, the variance, and the standard deviation. So I'm going to go ahead and click on this box right here. By clicking on that box, I'm going to have all of my data brought into StatCrunch for me. Okay, and then I'm going to go to Stat, Calculator, Custom. I'm going to put the dogs in for my X variable. I'm going to put the, and then the probability in for the weights. I'm going to hit compute. When I do that, I get my mean right here, and I get the standard deviation right here. So the mean is 0.598. I'm going to round that to 1 decimal place, so that would be 0.6. The standard deviation is 0.9666664. They again want 1 decimal place, but make sure you come down here. So the standard deviation is here. That would round to 1.0, but they also want the variance. Well, StatCrunch doesn't give me the variance, but that's okay. I can take the standard deviation, but I know it worked for this one, but it doesn't always work. When you go to put this in your calculator, make sure you go a few decimal places. I went 4 here. 3 is probably good because we don't want round off error. So take the 0.966, square that in your calculator. So in your Casio, go ahead and square that, and then you would get your variance. So the variance is not in StatCrunch, but you get the information you need to find it. All right, let's do one more expected value. So in a game of roulette, a player can place a $7 bet on the number 30 and have a 1 in 38 probability of winning. Okay. If the metal ball lands on 30, the player gets to keep their $7 and get an additional $245. So we don't have to subtract like we did with that other problem with the raffle. Otherwise, the player is awarded nothing and the casino takes the player's $7. Find the expected value. Okay, so we have 2 things going on. Either they bet the $7 on number 30 and it really is number 30. So in that case, they are going to win $245 because they get their $7 back, but they only have a 1 in 38 chance of that happening, right? Because there's 38 slots on this game of roulette, and so there's only 1 chance of it landing on 30 out of the 38 slots. So otherwise, they're going to lose $7, so that would be minus 7. And that would happen for all the other slots. So there's 37 other slots. And so the probability would be 37 over 38. And notice those 2 together would give me 1. So what we're going to do is multiply those. You're going to multiply 245 times 1 over 38. You're going to multiply negative 7 over 37 over 38. And when you do that, you get negative 0.37. So again, you're not going to lose 37 cents at one time because you can't. You either win 245 or you lose 7. But over time, you would win some of the time, lose some of the time. And so if you played over and over and over again, your average loss would be 37 cents.